Modular programming. In this nugget, I'm going to teach you how to make your Python programs more robust. The chief way to do this, among just being a great Pythonista with your own code, is to extend your program across one or more modules. So I'm going to teach you all about imports in this nugget. In so doing, we're going to have to deep dive into the module search path, and then we'll finish with a brief consideration of Python packages and also distributing your finished Python applications. Now, this piece will certainly be new, but we've been using modules all course long, so this isn't going to be all that much of a surprise, and we've even touched on the module search path, namely the sys.path variable, multiple times as well. However, I think that this nugget should be especially useful to you as a Python student because it should tie up loose ends and really tighten up that conceptual framework that we've been building. Let's get to work. Question of the day right now is, what are Python modules? At its most basic level, friends, a Python module is simply a plain text file that typically has the .py extension that contains one or more lines of, you guessed it, Python source code. Now, as we're going to learn very shortly, there's some other extensions. For instance, there's PYC that are bytecode compiled modules, but anytime you hear a module, we're talking about a Python file. You might have an application that consists of just a single Python file. You might call this a script, or as your application becomes more robust, you might import one or more modules from the Python standard library or third-party libraries, and they become, by extension or by importation, part of your overall application. In this case, all three of these file objects are considered modules. Another definition of modules is that a Python module is a self-contained namespace of names. We now are very familiar with names, and this is Python's version of the variable as it appears in other programming languages. The kinds of names that you're going to see in a module file are things like classes. This is an object-oriented programming term that defines a blueprint for a particular data type or object. We cover OOP a little bit later in this series. The second component of most modules is the function. We certainly are familiar with functions. And then we have variables, global variables that may be accessible throughout the entire module file. We already know that you can define variables within a function. You're going to learn once you get to those nuggets that you can declare variables or names within class declarations as well. Variables also show up in modules as what are called constants. A famous constant that I'm sure you're familiar with is mathematical pi 3.14. You can access this value to a pretty long degree of precision just by accessing the standard library, but you may have other constants, in other words, names whose values are completely immutable and will not change under any circumstance in your Python application. Now, what are the benefits of modularizing your program? Everything you need in the program might be in just a single top-level Python module, but chances are if you really want to extend your functionality and not reinvent the wheel, you're going to probably wind up importing names from one or more supplemental modules. So therefore, a chief benefit of the modular nature of Python is code reuse. We don't have to worry about how to open a file or open a URL by programming that code in our Python source from scratch. We can simply import the appropriate module or modules and take advantage of those classes, functions, and variables that are already contained in those created modules. Another neat benefit of modular programming in Python is that we can share these modules, put them in a central location, perhaps on a network SharePoint, and your entire development team can transparently access all of the names contained within that shared component. As we're going to learn, the sys.path variable that acts as a Python search path for module files includes a subdirectory called site packages. This provides, by default or de facto, a shared location for installed third-party modules or user-created modules. Finally, and this is a big one, using modules in Python is helpful to avoid name collisions. I've given you this example before, where you might have a top-level file and then you're importing another Python module that you're using essentially is a library of classes, functions, and other just static variable or names. You may have a function called, let's say, fx in your top-level file. When you do your import, lo and behold, there's an fx function in this imported file. Now, how is the Python interpreter going to differentiate one instance of the fx function from the other? Well, my friends, that's the namespace concept coming to our rescue. What that means is, because a module is a self-contained dictionary of names. Now, I shouldn't use the word dictionary because we know what a dictionary is as a data type. But because of that, we could, for instance, have a top-level file named A and an import module named B. And because of this stacked hierarchical namespace, self-contained directory of names, let's look at it that way, the Python interpreter will never get confused because a call to a.fx is certainly different from the qualified name b.fx. Now, in just a moment, I'm going to show you the two chief ways to import modules into your Python project. I strongly favor one over the other, and the reason for that is because I'm not a fan of any situation that might involve a name collision or potentially overwriting a reserved name. That can sometimes happen in Python, unfortunately. Another gotcha that you need to be aware of, this trips up a lot of newcomers, is that module code is run on first import. So we have our top-level script file. We want to bring in some really nifty math functionality, let's say. So we run an import on this nifty new math library we created, and then we begin to see unexpected results like output of functions, etc. This is due to the fact, as I said, these modules, all the lines within that module are run on first import. Now, there's a way around this called the main trick. I'm going to show you that shortly, so we'll leave that go right now. And the final point I want to make preliminarily about imported modules is that they are compiled to .pyc bytecode files. So as you're working through the process of developing a Python application and you're importing modules from the standard library or elsewhere, a compiled or semi-compiled bytecode version of that imported file will be copied into your current working directory. This is nice, of course, because all of those classes, functions, variables, etc. have already gotten down into that intermediate bytecode format, so they should be picked up by your processor a lot faster than if the imported file had to be reprocessed from scratch every time you run your top-level file. Okay, so exactly how do we import modules in Python? There's two ways to go. Over here on the left side of the whiteboard, this is what we have been doing thus far in our training. If we need, for instance, different functions for traversing the file system, which we looked at recently in an earlier nugget as a matter of fact, we would call, in this case, the OS built-in standard library module by just using the import keyword, space, and then the name of the module. Now, we're not saying, for instance, os.py. Likewise, let's say I created a really nifty library file that contains functions and classes that I do want to have as a shared library for use by multiple Python programs. And let's say I just called this file lib.py. To make a call to import lib.py into my current project, I can type import space, but then all I need is the lib. We do not need and should not put in the extension at all, okay? Now, what happens when you run import using the import keyword is that anything, and by anything I mean all of the names, the entire namespace of that file, is now available to your top-level script file. The gotcha here is that the namespace of the imported file is preserved. So if I wanted to do a call to the change directory function in the OS module, I'm going to need to prepend the name of that imported module, dot, and then the name of the calling function, you see? That's again something that trips up Python newcomers, but I think you're already cool with that because we've used this syntax several times thus far. And this gives us what's called name safety, because the likelihood of a collision is essentially nil with if we imported another module that also had a function called chdir. The other way to import modules into your top-level file is to use the from import construct. Now, the way this works is we say from and then the name of the target module, import, and then we pass in a comma-separated list of individual names from that file. Some Python programmers like this because they feel it's a more memory efficient way to go. When you're doing import, you're grabbing all of the contents of that file and bringing them over and running that code. When you're using the from import syntax, you can go into the target file and pull out only the names and procedures that you want to extract. And again, those names are just separated by commas. One neat thing about this syntax, besides the increased memory efficiency, is that you can then call those functions without qualification. That is to say, if we did from OS import chdir, we can then invoke that function just by saying chdir and then passing in our argument, you see. Now the downside to this is when we use the from import syntax, the namespace is stripped away from those names as they come into your top-level file and are absorbed by the namespace of your top-level file. So you wind up with the potential of overwriting objects that are in your current namespace. That's why I formally suggest sticking with the traditional import syntax unless you're absolutely sure you're not going to have a name collision. Moving our way down this whiteboard, you see a kind of a schematic diagram of a multi-file Python project where we have a top-level file. This is the file that's actually passed into the interpreter or run by the user. In order to take advantage of external or extended functionality, you see we have two imports here, m1.py and m2.py, and notice the direction of the arrows here. You notice that these modules can communicate with each other as well as with the top-level file. And if we have Python installed on our system, obviously we do, we have access to all that 200 plus modules that we get with the default build in the standard library. Now this can be extended ad infinitum really by going out onto the web and downloading modules that other programmers have built, or alternatively, if you're a DIY do-it-yourself person, you can write library files from scratch under your own steam. Okay, let's begin some work with module imports. If we wanted to work with, say, the sys module, part of the standard library, we can do an import sys shownuff and then run, for instance, dir on sys to get a list of all of the names that are contained in this file. And you see there's quite a few, obviously. And we won't review it again, but remember how the built-in help works. We can run help and pass in any of these names, qualifying with sys, of course, to retrieve the documentation string for that name. You'll remember a couple nuggets ago when we worked with files, I told you we can do some what's called introspection, and this is a programming language buzzword that enables, in this case, Python to recognize aspects of itself or its surrounding environment. Therefore, if we want to call sys.platform, we can do that all day long, but remember with the rules of importing, we need to prepend the module name to the function name. That is, if I just type platform, I get a name error where Python tells us that the name platform is not defined. By contrast, you'll remember the other way to go is, for instance, from OS import chdir if we want to bring in that function. And you'll notice that if we do include the parentheses in our import line, we're going to get a traceback, just a simple syntax error. It's important for us to know that the way the import commands work in Python is that we neither use the .py extension nor do we use the parameter parentheses with our names. So now that we've taken the chdir directory out of its original context and we've absorbed it into the current interpreter's namespace, we can use the command without prepending the module name to the function name, like so. Now, if I try to access another function from that module, we get a simple name error where the Python interpreter tells us that it doesn't recognize this name. We're in a pickle. Take-home message, if you're going to use the from import syntax, make sure you've imported all of the names that you need, okay? Now, here's another trick that I think you'll like a lot. Oftentimes, when you're developing your Python programs, you're working interactively in, say, the idle or Python shell environment, and you need to reload a Python script file that you've been working on, or you just want to reload a module into the current, what you see here, an interactive session. The way you can reload a module in Python is you first need to import the IMP module itself. Now, if we run help on IMP, the documentation string says that this module provides the components needed to build your own import function. Well, that's all well and good, but what we can use here in your script files or interactively in the Python shell is that we can call imp.reload to reload any module back into Python. In other words, to start fresh with it. it. This can be especially helpful for iterative program development. Therefore, if I have a user-created module that I want to reload into the interpreter, I can do imp.reload and then pass in that module name. Now, you're going to potentially run into some troubles here if you're trying to reload modules that are only partially there. You'll remember with OS, I imported selectively and only brought in chdir. If I try imp.reload with the sys module, we get the feedback module sys and it tells us it's built in. But we could just as well do this to rerun a script file that we created ourselves. No problem. Now let me show you another Python hack. This is called the name trick. And this is a way to get around that fact that when you run an import space module name, the Python interpreter will parse that file and run all of the code within it. Now that's what you would want perhaps if this were a top-level script file that actually constituted your main application. On the other hand, if this .py file is meant to be used as a library that is going to be imported into another project, we don't want that code to actually fire and run. We want it parsed, we want it cached in memory, we want it brought down into bytecode, but we don't actually want to interrupt the control flow of our application. So how do we get around this problem? Well, here's what you do. You can take two internal names, internal Python names, and run a quick test. Normally what Python programmers do will put this simple if statement at the bottom of their script file that they want to use either for dual purposes, for running normally, or as an imported library. And what we're checking here is that the internal name that references the name of the current Python file, if that name equals main, main, this is an internal name that's representative of the top level file in a running Python program. So if the file that's running now is the top level file, then you could run your code. And what a lot of programmers do here is they'll put some kind of documentation routine or a testing routine. This can be useful for what's called unit testing your code when you're running the program as a top level, as a main file from the operating system shell. And when you do this, your functions, your variables, and all that stuff are not actually going to be injected without your permission into your running top level file if you bring this file in as an import. So in this sample, I have a py file called square math that contains a very, very simple function that takes one argument, an integer we presuppose, and will square that integer. So if we bring in 2, it's going to return 2 times 2 equals 4. So we should be able to go to an operating system prompt and type python space squaremath.py. And in that case, because the name of the file, squaremath.py, is equal to the main top level file that's being run by Python, the result of that operation should be testing square of 2 equals, and then we test that the function works. By contrast, if we are in another top level file that's going to have its main private name identifier, and we run import square math, in this case, because we've performed this nice test down here, the file will be available. Our square function will certainly be available in the top level file, but we'll suppress this diagnostic business down here, and we won't actually return any values without our permission in that top level file. Now let me show you what this actually looks like in Python. In this sample script file that I've named modtest2.py, all we're doing here is running the name hack, where after our shebang exec hack and our module documentation string, we're running a test for name and main, and if we are running modtest2 as a main program, we should get this result back. This program is being run by itself. Otherwise, if we're doing modtest2 as an import to another top-level file, or if we're in the interactive shell, we should have this code run. I am being imported from another module. Best way to test this is to test it, right? First thing we'll do is switch on over to the Python shell, and I'll run import modtest2. I am being imported from another module. That's what we expected. By contrast, from the operating system environment, if we run python modtest2.py, this program is being run by itself. You see, this is a really useful hack, everyone, in terms of making your code more portable. In other words, being being able to use it, for instance, primarily as a library file that'll be imported into a top-level program, but also you could have diagnostic code here such that when you run the file as a top-level file, you can have that code run just to educate yourself on how the module works, or just do unit testing, as I said earlier. Now would be a good time, actually, to show you the reload command in action. Instead of ping-ponging back and forth after we make some changes, let's say, to our modtest2.py file, we might want to reload this module as an import into our top-level file, or especially now in the Python shell. Let me show you how that works. We can, again, it's a couple steps. We first have to make available the imp module, and then call imp.reload, passing in the name of the module that we want to reload into memory. And there you have it. Let's look at another simple example. I have a file called modtest.py now. And what we're doing here is basically replicating what we saw on the whiteboard several moments ago. I have a very simple function declaration. The function is called square that returns the square of a given integer, and we're returning x times x. No big deal. Now, our safety is preserved in terms of using modtest.py as an import library and not worrying about infecting our top-level file with code that we don't want to run until we need it to run. We have our name hack down here such that if we run modtest from an operating system environment, we're going to just print out testing and then run the square function, passing in 2 as an argument, just as a sample. So here we go. We'll simply hit the up arrow to invoke our last command from the command environment. I'll run python modtest.py, and there's our testing result. If we come into the Python shell, we can import modtest, we can run help on modtest to get the documentation string, and then finally, and most importantly, we can run modtest dot. There's our sensitive help, our context-sensitive help giving us some instruction. We have square, and I'm going to pass in 10 here, and we get 10 times 10 equals 100. All well and good. A very appropriate chicken versus the egg question that you might have now is, how is Python finding these modules? I'm having fun all day long running these imports, whether we're using the import statement or we're using from X import Y. The module search path needs some revisitation right now to make sure we're really clear on it. The purpose of the module search path in Python is to simply make your module imports as transparent as possible. Now, if you're in your development environment working alone or with a team, you'll want to make sure that if you are working on separate computers and you're not sharing resources, that you're able to share your project files with your colleagues and have those imports work correctly when your colleague runs your code. You see what I mean? So there's the possibility of creating a shared library up on a server somewhere, and then getting back to Earth, so to speak, there's the question, how does Python actually resolve those module names? We can look at the module search path as kind of a hosts file, in a sense, if you're familiar with TCP/IP networking, only we're looking for the location of PY modules. Now, a little bit of review from earlier in the course. The way the module search path is created is first and primarily in the operating system environment. So you're going to be using the export command, for instance, in Linux, Unix, or in Windows you can use the path statement from a command line, or you could use the set statement and the path keyword in a Windows command line environment, or if you're a GUI person yet in Windows, you can use the system control panel. And you'll want to create an environment variable called Python path and pass in as many directory locations as you need to get to your standard library modules as well as any third-party modules or packages. Now, what happens when you fire up Python is that the interpreter populates an internal system variable from, you guessed it, the sys module. The variable is called syspath, and what this name is, it's actually a list. And you know, I hope you're thinking Pythonistically now, because syspath is an ordinary list, we can run ordinary list methods on it to do appends, removes, etc. to modify that module search path. So what's neat about this is that you can, in your Python code, put in a append method, for instance, to pop in a custom directory that might exist up on a server, such that you and your colleagues would always be able to find those support libraries. Now, the thing to remember about syspath and editing that path in Python is that its lifetime is only the current session. So if you restart the idle shell or cut out of the interpreter and then get it back going again, you're going to lose any edits that you've made to syspath. So this is very dynamic, volatile data. If you want to make permanent changes to your module search path, you know you have to change the Python path environment variable in your operating system. A lesser known way to go with module search paths is to create a file with a PTH extension. This is what we call a path file. And this is simply a standard text file that contains one column of information, and these are simply directory paths that Python will parse, will resolve, and add to sys.path every time the interpreter is fired up. Therefore, you've got some flexibility here. On the hard-coded side of the fence, we have Python path. That's a pretty putting cement down, laying a hard foundation on where Python is going to go to look for modules. To be more dynamic about it, on the other extreme really, we have sys.path that's recreated or reset to Python path every time the interpreter is restarted. And then as an intermediate middle road, we can create a simple file, give it a path extension, put it in, say, your Python 31 directory, your Python installation directory, or another place it can be put is the site packages subdirectory. And every time the interpreter fires up, it will add those paths to the module search path. Final thing I want to say about the module search path is that Python does parse those directory paths sequentially in the order in which they appear. So for maximizing performance, I would recommend that when you set your Python path environment variable, you put those paths in descending order of frequency. That is to say, directories in which most of your modules occur, for instance, C, Python 31, lib, etc., are at the front end of the path, and less frequently used directory paths are put in the back of the path or not even added to Python path. Perhaps you can put those in syspath or even a path file. Let's spend a moment looking at the search path in Python. To look at syspathlist directly is pretty easy. We know the deal. We can import sys and then simply echo back sys.path if we don't want to perform any operations on this. Again, it's a simple list that contains, I don't think I've changed this at all, these are all default locations that come to us courtesy of an installation of Python 3, but also I have installed some third-party packages. So you'll see, for instance, this guy right here, Python 31 lib site packages Python Win. That's the Py32, Python for Windows extensions. They've added a permanent entry to the Python path variable. Nice thing about idle that I've showed you before and yet I'm going to show you again is from the file menu we can open the path browser, and this shows us the current contents of syspath, which we already have down here. Now what's nice about this GUI element is that it makes it easy to drill in to these folders to see what they contain. The downside to this is that this is a read-only list. Okay, so we can drill into lib site packages and see some stuff going on here. There's a package, and you can get right down to individual PY files. And yes, you can double click those PY files and view them in idle, as you see right here. As a student of Python, I actually recommend you do this. Browse your syspath in the path browser, find modules that are helpful to you, and open them right up. I'm sure you remember this guy, PyDoc. You can look up modules and get data on all of the names contained within any of the standard library modules by firing up PyDoc. If you're not watching these nuggets in series, shame on you. Just kidding. But you might want to go back and check those out. Alright, so this is all well and good. We'll be talking about packages in just a minute. You notice under C Python 31 lib, we have a whole bunch of packages that come to us as part of the standard library. Don't expect you to know the difference between just a single PY file and a package. You notice this is actually pretty cool too. I want to draw your attention to this. The Path Browser allows you to crack open individual Py modules to take a look at what they've got going on inside them in terms of function declarations, etc. Double-click the function declaration, and you can actually be brought to that location in the file. Isn't that great? Especially for learning, this is really good stuff. Now, if we wanted to temporarily, or just as far as this session is concerned, modify the syspath, we can do it directly. Remember, lists are mutable. So we can just do sys.path dot, and I'm going to append the path C files to the list. So now if I echo back syspath, we see that C files has now been added to the path. Of course, what this means is I can create a module, put it in C files, and now call it in my code, at least for the lifetime of this session, using either import or from module import X, Y, Z, etc., how that works. One thing I find a little interesting is I reopened the path browser and I'm not seeing that append added to the GUI interface. Oh well, you can't win them all. Now if I restart the shell, which gets rid of anything in memory as far as names are concerned, I run import sys again and echo syspath, you'll note we're back to where we were originally, ending with Python win, and C files is gone. A detailed consideration of Python packages and distribution methods is unfortunately beyond the scope of this training. If you are interested in these subjects and other more advanced topics, please let CBT Nuggets know, because speaking personally, I would love to put together an intermediate to advanced level Python training course as well. Now, what is a module package? And how is it different from, say, a single or multiple separate PY module files? Well, what's cool about packages, friends, is that it organizes or makes it easier for you to organize and ultimately distribute your Python application. Simply stated, a module package is a collection of one or more folders that contain one or more modules. So you might have a top-level file and several files that you use as libraries. Some of these could be from the standard library. Some of these could be ones that are homegrown by yourself. Now, would you rather just give your user this entire bucket load of files and say, okay, go have fun? Or would you like to create a package which makes it much easier to interrelate all of those files and make it easier yet for the user to just transparently make use of your Python application? I thought so. You want to know about packages, don't you? In my opinion, the best way to get started learning about these things is to visit the online repository of community-submitted Python packages. Now, the standard library gives you a lot of functionality. If you want FTP, it's there. If you want World Wide Web, opening up web pages, it's there. On the other hand, if you want to do advanced work in, say, SharePoint, access some more advanced Microsoft Office stuff, or even off the Microsoft and Windows reservation, going into media with Linux and Mac, etc., you might want to visit the Python Package Index, also called PyPy. You like the name? You can browse the packages and download what you like. Let me show it to you really quickly. So we simply visit pypy.python.org/pypy. Tells us we've got, at least as of this recording, in early May 2010, almost 10,000 user-submitted packages. There's instructions on how to install the packages, and then we see a list of recently submitted ones. There's something that works with the Django web application framework. We're going to talk more about that later. Zope is another Python-based web application framework. Really good place to go and check these out. It's going to put your Python development on a much faster track if you leverage what other folks have already done instead of trying to, again, reinvent the wheel yourself. Now, just the ground rules about creating your own packages. What you're seeing here is some really nice sample code from pythonconquerstheuniverse.com. Basic, highest level view of a package is that you have a top level directory with the name of your package, and you have a top level file called _init _. This is your main, shall we call it a bootstrapper file, from which all of the other related modules in your project ultimately resolve. You can set global parameters for the running of your application. You could link to subdirectories. Now you'll notice that if your package is more than one level, it actually reminds me of a line from the Zen of Python with regard to flat versus distributed file and folder structures. I think the Pythonistic way is that we want no more than two levels, a top level and maybe a second level, but nothing more than that or it gets too complex. But you notice that in this parent package, we have our global init file, and then we have several support libraries at that same level. That's great. Those are going to be referenced in initpy. And then there's a subfolder called feeding that contains its own init. So in each directory has to have its own initialization file, and there's eating and drinking inside of that subdirectory. Now, how does this work? Well, you basically want to give your users this entire ball of yarn. In this case, you'd give the user parent folder that contains all these other PY files. The user would put this whole folder in their, say, site packages folder under their Python installation folder, and then it'll just work. They can start running imports. For instance, they could do in this sample, import parrot that loads the entire project by using the top-level init.py bootstrapper. Import parrot.talking is going to dip down and just grab names out of this guy. Import parrot.feeding, same thing. That's where we're dipping into the folder and initializing here. And then you can still use the from syntax as well. Does that make sense? Good. Now, once you have your package all ready, you might be interested in distribution. Distributing a Python package brings up so many questions that are unfortunately beyond our scope at this point. But stuff like what's going to be the easiest way for our users to actually install this on their system? The most orthodox way to go is to use the built-in dist utils. This is itself a package that comes with the standard library in Python, and the net effect of using the dist utils, the distribution utilities, is that you wind up with a setup.py file that your users can simply run. Let's look at it as a Python version of the install shield, or in the Mac world, the Wise installation. You see what I mean? Setup.py is what you typically wind up with dist utils. The other way to go, the more familiar way, especially for Windows and Mac users who are almost exclusively graphical in most cases, is you can use py to exe to create a binary Windows installer or installation routine. There's also py to app that does the same thing. It creates a binary installation package for use on Mac OS X systems. Before we finish up here, I want to bring up the Python shell again and also open the file menu and bring up the path browser just so we can dip in. I want to show you under CPython31 lib site packages. This is, as I've said earlier, a good generic location for folks to put their third-party packages. A lot of times if you're using dist utils, you'll specify in your installation Python script file where the package will go. Site packages is a nice place to put it because you know that any user running Python is going to have a site packages directory in their sys.path variable. You see what I mean? So the imports will just work. And you also see in this case, we have, at least on my computer, several packages under site packages. Python Win, and you notice if I open up the package folder, boy, it just goes on forever. Debugger is a package, Dialogues is a package. Python Win, or PyWin32, definitely seems to not obey the Zen of Python rule about flat is better than stacked. Ultimately, if we open up a package folder as promised, we're going to see an init.py file. There's our run of all of the function declarations. That's our bootstrapper, and it looks like this particular debugger package consists of 5 script files in addition to init.py. Let me open up init.py just for grins. And it's basically setting up the environment. Some cruft to deal with, blah, blah, blah. So we see some really nice user-friendly comments here. Basically initializing the environment for debugging. Modular programming review. Now that we've completed this nugget, I'm hoping that you're feeling really comfortable with what modules are and how the import process works and the ramification of that process as well. I hope you're also really comfortable with the module search path. I hope you're really specced up and spit-shined, so to speak, on the sys.path variable and the several different methods that we can use to modify the module search path in Python. And third and finally, we looked at Python packaging, and we did a very high-level overview of distributing our finished Python projects. I hope that this has been informative for you, and I'd like to thank you for viewing.